Awesome. So this is discussion 114. My name is Kevin Kocek. I'm the founder CEO of Chemical Q Device. So this is for how to conduct medical R&D with QiML, quantum-inspired machine learning algorithms and architectures. So I'll be going over a lot of this as far as like laying the framework of demos that you would use. So this is Thursday, December 21st, 2023. And in specific, Qiskit does have a number of these machine learning demos. And by these, that typically means either you have some quantum embedding or a trainable variational quantum algorithm, and some of them are very well done. And so I included effective dimensions, torch connector, and the QGANs. And so basically, Qiskit and PyTorch are together with this. So as far as we know, there's no way of using GPUs with PyTorch plus either Qiskit or PennyLane. So that's an issue that would have to be addressed coming up. And so for the second one is if you want to start running today, so you have your own medical images. I ran up to say 4,400 of these. You definitely want to check out, it's the PennyLane Quantum Transfer Learning Demo. So this one was actually done by Andrea Marie, and it, as far as like coolness factor, what you can do with it, changing the algorithm, you can also change the ResNet, which also, by the way, takes up most of the compute time and resources over the quantum algorithm. So the GPU, say for instance, in Colab or something like this would work, but it's not going to work for the quantum circuit because of the PyTorch thing. So there are PennyLane demos such as this equivariant graph embeddings that are NumPy and PennyLane, and you can go to town with as many benchmarkings as you want. And I've done a fair number of studies with that. There may be other advanced settings, with NumPy that you could do neural networks, but traditionally these are, first done with like Keras or PyTorch. And also this other demo, this generation in QML, this was some Caltech and Los Alamos National Laboratory individuals. And basically this is one of these, quantum benefits of, not having to use quite as much of the training data to check out as well. And then lastly, it's the most promising, I would say, of the bunch. Is this parallel quantum circuits. There's two demos on PennyLane. There's a PyTorch and there's a Keras. And the Keras doesn't work quite as well, as far as having to install other stuff and getting rid of, warnings and errors and stuff like that. But the PyTorch one runs pretty well. And like I said, you're going to have to stick to like a high RAM CPU for the time being until all these, the PennyLane PyTorch or even the Qiskit PyTorch, things get worked out with using GPU. So I'm going to present on some new results with that, basically requiring significantly less RAM and significantly less time to do classification tasks. So here's the first one. So they say global and a local effective dimension is a dimension capacity. So this is more, fundamental study, but ideally you can make these modifications to the different algorithms. So say, for instance, the first, in this case, you want to go high, with effective dimensions. Now, there's been some ties with this, with overfitting. So say, for instance, you get the highest, effective dimensions. And same thing with, say, for instance, quantum metric learning or training and embedding. But the parallel quantum algorithms, which I'll get to later, kind of addresses some of that. So you'll see these, basically original first, second iteration, these notebooks, and you'll see the numbers below. These are up on the repository. So, different things were changed to get better results for that. And also another one is this MNIST, it's a torch connector hybrid QNN, a Qiskit demo. And in specific, you can try to get this lower loss. So going from like a negative 1.7 to negative 7 to negative 7.5. And, these demos provide a good kind of foundation. So a lot of times you can go MNIST. I know for sure in Keras, you can go to fashion MNIST. If you want to go to color, that's like a CIFAR 10 or CIFAR 100. But these are good foundational demos from Qiskit to take a look at. And they're well done. They haven't been updated, I would say, in a while. And, there's 12 of them, and say 11.5 out of the 12 works. One of the, I think the last one has some issues towards the end of the demo. So here's another one. It's basically these quantum GANs. So it's the same thing. It's a generative adversarial network, but with quantum algorithms. And basically, you can change things such as shots, and you can change, to try to get this lower entropy, that keeps going down by changing things such as the learning rate. And a lot of these, if you've mastered machine learning, this is for you. Now you just have quantum algorithms, okay? And some nuances with it, but if you understand batch size, learning rate, these types of modifications, the types of data sets, you're in good hands. And then, so here's this other one. So actually, I think we went over this. And then, so the quantum transfer learning one, if you're listening live or you're watching on the recording, you have to check out this demo. It's just so cool. So it was actually 2019. Like I said, it still has the issue with the PyTorch, Penny Lane, the GPU support. The GPU, I recommend running because it'll run with the ResNet, but the QPU itself yet has not been supported, with Penny Lane and PyTorch. So you can upload pretty much any data set, and it actually says this in the demo. So it starts with ants and bees, and I went from 2 class to 4 class to 10 class and 44 classes of brain tumor MRIs. And the net result is basically it's a little bit better. It struggles with the same thing as if you were to run huge quantum circuits. So say, for instance, on this particular one, it's requiring 88 qubits for 44 classes of my data set. And I never got to that point. But I think with the parallel quantum circuits that I'm getting to, I can get a lot closer to that, and especially without this exponential RAM and runtime kind of thing. And so here's an example of basically comparing it to 3 other classical models. So the one that was most closely related to this is basically the ResNet, or the convolutional neural network. It's a conventional, convolutional neural network, classical, traditional, is basically that those weights are frozen. So what additional benefit do you have in adding a quantum circuit? So this is like, I get people, message me on LinkedIn that they want to do this specific thing. And, this, like I said, you cannot go wrong with this demo. Just don't expect to run full blast GPU, on the quantum simulator. But I do recommend running it because the ResNet takes up more of the resources than the quantum algorithm, unless you go really high with the quantum algorithm. And then here's one to do benchmarking. So this is NumPy and this is Penny Lane. So basically, I did this extended study with it, and pretty much, I don't think at this point I did the lightning.cocos, but the Penny Lane big ones are called lightning.qubit, or default.qubit, lightning.gpu. And then if you go lightning.cocos, that opens up, if you're on CodeLab, 3 GPUs, and then a CPU and a TPU for 5 more. So anyways, these are the types of models that, either that needs to be a fix, with the PyTorch, Keras, and, Penny Lane, Qiskit to enable GPU support, or, we just start doing everything in NumPy and Penny Lane. So if you're looking to, do graph embeddings, if you're medical field too, this is a nice demo to check out because you can go fast with it. So, and here's some of the speeds. So I think it came down to like a lightning.gpu. Actually, this one does compare lightning.gpu A100, which is the top you can get on Colab now, 40 gig, but you don't need nearly that amount of RAM. It's about, some orders of magnitudes, greater than, say, for instance, like a Qiskit.air. And actually, I didn't include the default.qubit and QLAX simulator. So anyways, and I'll show you why it's important to run efficiently. If you can't run efficiently, if it's just taking all day to just do a single experiment, that's not efficient. So you need a data set that's fast and then scale up after, a certain point. And, it's just, and you have to know which devices to use and which demos. So, and for quantum machine learning, for medical data, you've got at least 27, I think, for Penny Lane. And for Qiskit, you have 12. And here's the demo that I was referring to, is basically this generalization QiML from Q training data. So the Xanadu/Penny Lane researchers, they recommend this one as far as getting this quantum benefit. So this is definitely worth checking out, and it's iteratable. And then, so what's leading into all this, and again, you've seen the post likely on the LinkedIn here, is basically for classification tasks, you don't always need to be like, so say if the quantum transfer learning model, you're running, 32 classes. Well, that model would run best at 64 qubits, but you don't have a 64 qubit circuit, especially to do with quantum machine learning. You might be able to get by somehow with a supercomputer, but you're talking like it gets very exponential, especially in RAM, and I'll show you some of these results. So this torch layer demo is basically this. You'll be doing, so say if you look at this upper right-hand corner, 2, 4, it means that each of these, so you have 1, 2, 3, 4 of these Q layers, and the values have to be correct, and the notebooks will be up, and you can also check those as well. Now, the core of all of this, if you want to do bigger architecture, so say if you want to do like 4 qubit, 8 layers, or if you want to do 8 qubit, 80 layers, you can do these types of things. It all depends on the core algorithm. So if your algorithm is not good, no matter how many different ways, it might actually get worse if you keep adding layers. So if you have a good algorithm, which isn't as hard to find as a single circuit. So, based on all the results, good algorithm, more flexible, broader range of good performance than a single circuit. So basically, there's 2 ways in this demo that things can be done. Is you could do this torch.nn.sequential, which is typically in series, or you could do torch.nn.module. And I wanted to further investigate these just to make sure if I run something that's 4 qubits in a single layer, and then in that same, this Thomas Bromley model, in my, if I want to run 40 layers with those 4 qubits, those both, the single circuit at 4 qubit and then the 40 layers or 40, parallel algorithms, they both run in the same model. So there is a performance benefit, this shows, of running in the torch.nn.module. Now, this is the main ones that's associated with doing neural networks. So say, for instance, this is, self.init, and then you also have forward, this forward function as well. And, what both of these showed is I fixed, these are all 4 qubit circuits. So the first one is 4 qubits, a 1 gate, 2 gate, 3 gate. A rotational Y embedding is an embedding gate. And for both of these, whether it was sequential or whether it was this module, is that they were both optimized at 3 algorithms. So if you look in the right-hand corner here, is basically you have a 4 qubit algorithm, okay, that's represented by the 0, 1, 2, 3 wires. And then the 3 RYEs are the layers. So it's similar to deep learning. And effectively, we might not even have to go much further than running parallel circuits because the quantum algorithms themselves, can be considered this neural network type of field, just like deep learning. So you'll see the 1 layer vertical, 2 layers vertical, and 3 layers vertical. The number of neurons matches the number of qubits. And in this case, it's a single circuit. So there's only 4 neurons for this specific one. So all of the data goes to that specific one algorithm. Now, this next one is basically hopping up to 8 qubits. And this is expected. So typically, when you go from, smaller, 2 qubits circuits, you don't see a ton of. But when you go to 4 qubit circuits, a lot in literature, and 8 qubits, you see the performance bump. So if you look at the top purple represents accuracy, and the bottom ones represent the training and validation loss. So low loss typically corresponds to this high accuracy. So it just depends, because some of these sequentials for the 8 qubit, there were 2 that were high. And then you see the one here, it was just 1. But overall, the performance was broader, using torch.nn.module. Okay, so these are, again, these are just single 8-qubit circuits. And then I did half sequential, so sequential method with torch processing. And I did half using module. And then you see, so, the torch.nn.module was better, whether it was a 4-qubit single circuit or an 8-qubit single circuit. And you'll see with this next one is basically, this is, torch training loss, validation loss versus quantum architecture. And, I'll go through, I still got to fix up some of these, the bottoms. But basically, in this specific case, it's now that I figured out what the best algorithm is, I'm going to go ahead and start to scale. Okay. So you'll see these first three are actually, the first two are sequential, but then you see 1 layer, 2 layer, 3 layer for 4-qubit. That goes up to 8 layers for this 3 rotational, the circuit that worked best, from the previous 2 studies. And you'll see that the lowest loss here corresponds to the most layers. Now for the 4-qubit, the first couple layers did not follow that trend, but eventually over the course of time it did. So the point of the story is if you start off with, say, an 8-qubit circuit, it's going to tend to have better, tolerance, as opposed to the 4-qubit circuit. And then likewise for the 8-qubit circuit, it actually, every single one from 1 layer all the way up to 8 layers, this is decreasing in loss. So that's more favorable here. And you see the convergence between training loss and validation loss. So what I put up here is this last circuit. It's, what I put up here is this 4-qubit 8L 3RY. So the 3RY is the algorithm, okay? And then the 4Q8L means it's 4 qubits, and there's 8 of them in parallel. So 8 times 4 requires 32 neurons, in the code. And you can see the code, examples of this too. Now, this next specific one is basically training loss, validation loss versus epoch. So this is a standard overfitting plot. So this is for 4 qubits. And the ones to look at for, and again, I'm not comparing with sequential. I'm basically, all of these are module, which is, you can't do parallel algorithms with sequential, but you can do a single circuit with module. So basically with these, you see the 4-qubit single layer compared to the 4-qubit 8 layer. So this burgundy and black, those, wind up with a higher loss. And then the 4-qubit 8 layer, so 8, having 8 layers instead of a single circuit. So it's a single circuit plus 7 additional in parallel. You'll see that these two, and especially the green, is the lowest. And the whole point is you want to see convergence. Typically in these, we start with higher training loss than validation loss. But you can see that for the single circuit, the red and the black, or burgundy and black, those, it wasn't as predictable throughout the course. So 1 epoch, 2 epoch, 3 epoch, these go up to 6. But you see for the yellow and the green that pretty much, you start at 1 epoch, and then the second epoch, it's a very reflective curve. And I just noticed this a lot is basically, you'll see this is running single circuits is, just the fluctuations. It has less tolerance, right? So it has less tolerance for going big in algorithms, and, it just doesn't work as well as the parallel algorithms. So this next one is basically, so this is the 8-qubit version. So this is 8-qubit single circuit, meaning 1 layer, versus 8-qubit 8 layers, meaning 8 algorithms in parallel. And you'll see, so these are looking at these, these Berkeley colors here, this blue and the gold. You see at this point here, they're not supposed to cross paths, right, in an ideal world. And they wind up, similar convergence, but at higher loss. But this is a good textbook example of something that converges better with more parallel algorithms. So you see with the 8-qubit 8 layers, this lighter blue, and then this gold, this darker cold color, like every single epoch, they behave predictably. And then you'll see the final convergence, even though there was a little cross at 5, very close to each other and at a lower loss than with the single circuit. And then, so I took this further and continuing the study, and all of those were done on what's called the it's called the Make Moons scikit-learn data set. So I said, what if I double the noise and I ran my best algorithms? So my best algorithms in this case is add 3 more rotational embedding layers, which are these last 3 that weren't, because that was 4, or actually that was 3 before. Yeah, that was 3. So I added 4 to the original 3, and then it's the closest thing to what I was running before. Validation loss 0.0426, validation accuracy 96. So it's harder because if you see some of these orange dots, they're not actually, it's definitely not, this data set is not linearly separable. And especially when you double the noise, you have this convolution, you have this orange dot here, and then you have these blue dots here, and you can almost predict which ones continue to get misclassified. So the second one is I did a Hadamard gate, for superpositioning, and 4 rotational embedding gates. And in this specific case, for 0.2 noise, I got the best overall, the lowest loss for this data set. And, the validation accuracy 97.5. So, again, I still have to research exactly how difficult this second data set is, but using traditional techniques without getting super fancy, it's like I said, it's like, that second or third step where it's even the first one's not linearly separable. And then also you have this, the data is kind of together or clustered. And then this last one, so basically I'm trying to run more rotational trainable gates. So this last one represents, a true machine learning approach to this. Now with classification, embedding is very important. So all these previous studies are typically just they're variations on the embedding layer. Now I have had success in 2 other studies where adding additional trainable gates, meaning this is making it quantum machine learning or artificial intelligence, assists the embedding already. Okay. And in this case, with this basic entangler layer, I can set it to, X, Y, Z, whatever I want my basis to be, and it has C0 gates. And the RX, RY, or Z in these cases are trainable, meaning they're just like, machine learning parameters. So anyways, when I ran this, I got similar results to the one, just the HRYE for the embedding, as opposed to the HRYE, these 4 embedding circuits with these other trainable portions as well. And so similar accuracy, but a lot of times the entanglement is not the greatest. So we're talking C0s or CZ gates, these types of things. And it's typically have a really good embedding and then also do some trainable layers after that. Now, where this all sits is basically the original study's done, and I went pretty high with layers to the 64x. So today's studies that I presented was the fundamental, right? Like figure out the difference between sequential and module, and then scale up from 1, 2, 3, 4. First with algorithms, and then with layers. And in this case, this is basically the second time, it's been observed that increasing the number of layers decreases loss, pretty much across the board. And if you run something small like this, like these 2-qubit circuits, you could still get, pretty good loss. And it actually got 100% on this easier data set with twice as much data, but it was better. It could separate better. So yeah, here's another example of basically increasing the number of parallel algorithms to decrease loss, right? And this is really important because basically, if you look at the 16-qubit 1L, you say it has a good loss, and it should, and the 4-qubit 4L has a similar loss. I think it was a little bit higher, but based on my setup and, what all I could do, if I have 51 gigs of RAM and this I think was using like 32. So 32 gigs of RAM, something like that for the 16. So anyways, what running these algorithms in parallel allows you to do is to keep going, right? So if you look at 4 times 10, that's 40 effective qubits for classification tasks. And you see that the loss is now under the 16 qubit one, and a 4 by 10 runs a lot faster than a single 16 qubit circuit because runtime and RAM are exponential in qubits. So that's why, I mean, if you had a good system, you could do 12 qubit, in parallel. If you have a really good system, 16 qubit in parallel, but I'll show you in the next slide that it's more linear. So towards the end of this 44 qubit 80 layer circuit in parallel, which is 100 or 320 effective qubits, is getting this much lower loss than what you can get at a 16. And this 4 qubit ADL is I think it's slower than the 16, but it takes up, it's the fraction of the RAM. Okay. But you can go up and up and up, and you basically, you want to have a rationale in doing these things, but trying to get to these lower losses, you can by simply increasing the number of layers in many cases. Now, here's the RAM illustration of that 16 qubit. So it's not an issue really at 2, 4, 6, or 8, or even 12, really. I think above 12 is an issue, where you really see the spike just because of the math of a 2 to the whatever, or 2 to the n, basically, kind of thing for qubits. So you could see that the RAM for a single 16 qubit circuit is way up there, so I said like 32 gigs. And then you also see here that the runtime's not terrible, it's not too bad for the 16 qubit, but to access those 16 effective qubits can be done with a 4 by 4 parallel circuit, and get a fraction of the time and like exponentially less RAM. And say if you want to go up to this 80, the one that I found that worked the best is it kind of, in this study, capped out at 4 qubits, 80 layers, is to as this specific one. And you can see that the RAM, it starts to get high, but it's linear, right? And then it's actually, the slope is steeper for time. Now, time can be addressed easier than RAM, right? Because we have all these massively parallel GPUs. So imagine even running single, quantum parallel one parallel algorithm on each GPU, like huge, algorithms, not surpassing like 16 or 20 qubits, but something like that. So anyways, it's a better problem to have this steeper slope of time, because this is on a high performance CPU. There's no GPUs being used in this study. And I think that's it for the slides. Are there any questions regarding the slides? So I see a number of people kind of hop on. And again, some of the figures like below, I have to fix up, so consult the final pitch deck, but the bulk of the slides should be up to date. Any questions or comments? And if you joined late, I would definitely say, in all of this, if you want something like a quick win, definitely run this quantum transfer learning model. It doesn't have the parallel algorithms baked in, but it's something that I'm working on to try to do. And you can run, your data in Colab or locally or however you do it. And, now you're definitely use a GPU, especially for the ResNet. And you can actually upgrade the ResNets like any other model. So there's like one other thing you have to change in a notebook if you go from like an 18 to a 50. And a 50 is more kind of modern these days. So, you can adjust the quantum circuit, and it's transfer learning too. So you come in with these parameters from ResNet initially, from the ImageNet model, those are set. And then, you're going to fix that ResNet. And there might be a way to actually train both your ResNet with your data and your QPU. But the way the optimizer is set up is it's set to optimize the quantum circuit in these. So it's months and months and months of figuring these out. But, basically, this is a good one. I would definitely check out the parallel algorithms too, right? Because, it doesn't really matter. Like these data sets, you can increase the noise or you can double the, data set size, these types of things if you need to. Any questions as far as it relates to, these specific models, getting into them? Because, it feels like, right, you might have seen the previous posts, the, multiple iterations of individual demos, that these could just easily take off, right? So you have NVIDIA, fully supporting the technology and running these massive, experiments, they got over 1,000 qubits. It's separate, but tensor networks with many hundreds, like 800 GPUs, stuff like that. And QCware, Classic, BASF, Terra Quantum AG. Terra Quantum AG actually has I saw a picture, and it actually said it has a picture of a chandelier, like some hardware, and it says that they're doing things the inspired way. And I had to really rethink all of this as far as like quantum algorithms, right? It's basically, breaking through and thinking of it as far as like accessing them in different devices. So say, for instance, like, that quantum algorithm, most of them can't get dequantized, meaning that they have some, special, quantum effects and superpositioning and entanglement and quantum interference. So they're very unique algorithms, right, that run on classical hardware and enable, it's a new generation of algorithms basically. And if you're not quite grasping all this, it's basically the future. And again, I ran all the parallel ones on high RAM CPUs, which are a little bit faster, more RAM. Your quantum algorithms, GPUs, and machine learning, right? So that summarizes the field of quantum-inspired machine learning. So it's just that extra component now with quantum algorithms. So, and again, I would encourage anybody that's in deep learning, machine learning, to really look into this, is because, once we start to say, okay, this is a really good study with, the parallel algorithms, because it's what it's showing is that it basically just keep increasing the layers and, the loss keeps going down, right? So, there's tensor networks, but they're approximate. This is exact. So these are state vector algorithms run in parallel, which give you exact answers. It's just now the input is spread across 4 different or 8 different algorithms. They all receive the same data, and it's a more efficient way of just getting to the solution more optimally and quicker. Awesome. So any questions? Any other questions regarding the slides here? And then anybody that we haven't heard from before?
Hi, Kevin.
Go ahead.
My name is Anup. I am not familiar with the work you presented today, so I didn't understand most of it. But I wanted to ask, like, where do I start? Say, if I want to look at the circuit models for ML, because I've seen some stuff related to basic circuits uh, before, and you kind of say things in the language where you separate out circuits and tensor networks. In my head, they are the same things. So I'm not sure what you mean when you say, oh, the tensor networks are more approximate. I mean, even if they are approximate, the circuit itself is a tensor network.
Yeah, well, we refer to a quantum algorithm being enclosed by a quantum circuit. So those two are interchanged. And then we separate tensor networks or say like parallel state vector algorithms, from these things too. But yeah, the quantum circuit, it's the, it encloses the algorithm, but it's not a tensor network. It's something different.
No, so the reason why I say that it is a tensor network is because we do have, the different propagators that act on different dimensions. So in some way, it is like a network of operations that we perform on tensors, which are, on different qubits, and we go from left to right. That is equivalent of, say, performing some, just say, if you look at some, say, matrix product state style tensor networks, or, we have some operators and we just keep going along some dimensions or a group of dimensions. So, I mean, I'm just asking this because I'm not familiar with uh, the ML side of it. I have seen some stuff related to applications in chemistry, especially in quantum dynamics for uh, nuclear problems, not with the electronic structure problems, but quantum nuclear dynamics. I couldn't understand a lot of it, so that's why I was like, let me just put it out there. Thanks.
Yeah, and I would, always don't underestimate because, I get caught up in models and I say, okay, the model's more important than the algorithm. But if the algorithm isn't right, it's basically doing the same thing wrong, over and over again, or I should say like less optimally. So I would start off, doing very fundamental studies, so one is just, batch size study, one is learning rate study. And then on the quantum side, and this relates to the other two too, you're going to have a layer study, like how many layers, in a lot of these models, they'll say like a Q depth or a number of layers, go 1, 2, 3, 4, 5. And same thing with algorithms too, get some algorithms from literature. I have a bunch too. And then just, whatever you're trying to do 10 different algorithms, right? But the more systematic that you can do and the more fundamental you start with, as opposed to like shooting for the moon, right? Like I just need to see how many layers to do. That's what I originally did. And then I came back to like a more fundamental study, like 0, 1, 2, 3, sequential versus module, those types of things. But that's my opinion, right? It's always run rather than research. And you will have to read, some articles and, some YouTube videos. You watch those too, but you'll learn a lot more, in my opinion, just by running and making mistakes. But it's not that much more. And I wasn't quite clear. You said you're in machine learning now?
Uh, so I I use machine learning models, but I do not develop them.
Okay.
Yeah, so I have used classical machine learning algorithms for clustering, and say now I'm also using this equivalent graph neural networks that you were mentioning earlier.
Yeah.
But yeah, but I'm using those for classical algorithms, not quantum algorithms.
Yeah, and it's surprisingly close to being a drop-in, that you wouldn't think it would, but basically all of these things like the QML.QNN.torch layer, everything goes from this quantum algorithm into a regular layer that you would have in torch.nn.module, right? Or if you're using sequential, either or. So, think of it this way. It's like, it's still classical data generating, classical data processing and all of it. It's just there's quantum mechanics behind these quantum algorithms, but it's still all bits. There's nothing else to that, right? So you're taking advantage of these, and we call it superpositioning, entanglement, quantum interference, that these bits are instructed to behave by, that the traditional algorithms today classically don't don't do that directly. So, and again, it sounds like it's very hard to dequantize or take the quantum information out because, that's the like, that's the basis, and it's hard to go backwards into classical because there's, no, hardly any other cases that can support that. So yeah, it's basically quantum algorithms plus just regular machine learning.
Okay, okay. I mean, I'll just have to learn a little bit on where do these things connect. So that's the part that I might need to learn a little bit.
Yeah, and if you've done, PyTorch or Keras, let's just say like PyTorch because it's more commonly used, is the optimizer loss function. Those are still at optim.atom or loss functions, just your cross entropy, loss, these types of things. And it's just in that specific section where you want to use this, new generation of algorithms, that's going back into classical bits. And this happens every single mini batch, going up to a full epoch. So,
Okay, thanks.
yeah, you're welcome. Anybody we haven't heard from? So, Renaud or Saket?
With Keras, you said so there are some issues, is it, Kevin? I think the first thing that you mentioned.
I'm sorry, I missed that.
Yeah, with Keras,
Uh,
you said you were facing some issues. Is that correct?
yeah, there's some issues. It's just less supported. So it's not even supported on Qiskit. And then on the Penny
Right.
Lane one, it's just, I had to install a previous version of TensorFlow, and then it just, it has some errors, associated with it. And for the most part, it runs correctly and it runs, predictably, adding more layers, but there are differences in, some of the performance that, say, the Penny Lane researchers say use the PyTorch.
Perfect. Either way, yeah, PyTorch is definitely the best. We're comfortable with it. Makes sense.
Yeah, yeah. So, that's how there's many of these demos. I mean, some use Jax, and if you want the very fastest performance now, it would be like a Penny Lane NumPy. But I don't know how hard it is to do, neural network circuits with NumPy. To say like Penny Lane is more for the quantum algorithm, and they have NumPy specific optimizers, stuff like that. But yeah, you can get the Keras one to run, but it took me a while to get the Torch one up to date because I needed, loss for training and loss for validation
Right.
on every epoch, right? In order to do overfitting studies. So that, that's why I was using Keras first, and then I fixed the Torch, which was
Okay.
just
No,
running
sir.
better. Yeah. But you'll see that if you look at the repository that, on the PyTorch ones that they're, they have, all the losses that you should need.
Oh, perfect. Definitely. Yeah, thanks. Thanks, Kevin.
Anybody else? So Ron or Mahmood? And then, feel free, holiday week's coming up. So, if you just want to wish a happy holiday, that's good too. And then Ron Quinn or Samuel? And Dino, and we could loop back again. So if you want to come back on, feel free to come back on. After all this that I've been through, I could tell you that it's not as bad as you might think it is. it's a classical world with quantum physics or quantum mechanics. And I'm kind of curious as far as, people coming from different directions too. Obviously, machine learning is a huge topic that people want to learn. So we could focus on that a little bit or as much time as it takes. So we have batch size, we have learning rate, We have the type of optimizer, we have the type of loss function, these types of things. And if you were to summarize machine learning in one, special sentence, I would say it's a bunch of algorithms that are continuously updated in order to get the very best answer. Because the optimizer, the loss function creates the losses, and then the optimizer sees that, changes things, and then that whole cycle is iterated in order, say, by the end of these cases, like the 6 epochs, to get the better, lower losses, higher accuracies, those types of things. So understanding the basics is really important, with machine learning. And on the quantum side too, is basically, all these algorithms, and we've heard from Sandbox AQ, Eric Schmidt of Google, he's a chairman at Sandbox AQ, basically says this is the direction of using, GPUs, quantum algorithms, and especially the CEO, so Jack Hittery, says, we're not even using, we're only using GPUs, with quantum algorithms. So it took me a while to break through all this and realize, like, this is just, it's a new class of algorithms, right? And they behave according to quantum mechanics because they're programmed to, because we know how they work, because we've studied previously. And that's all in these simulators. And so you can get this advantage. And there's a gentleman on my feed, I think it's Javier Montero, and he put up a, picture. It says, quantum inspired machine learning, a bitter pill to take. And that's kind of true, right? Because most people don't think of quantum algorithms like they're universal across devices, right? Because, the issues that we have running with a single circuit on CPU simulators appear to be, in this case, mitigated by running more parallel algorithms. So again, like, it's, you'll think one thing and then the results are saying others. So, and then what's in the future with all this is basically, other data sets too, and higher dimensions. Now I think, so the way these work is, it's not like, so you have, say, 32 neurons across 8 by, or 8 4-qubit circuits. Okay. So all of those quantum circuits get the same exact information. They're not different. They don't get individual data sets or whatever. Okay. So that's the parallel aspect of that. Now, I think to get, say, higher dimensions is you would have to, say, block off, 4 algorithms for these dimensions, 4 algorithms for that, because they effectively behave the same way as a regular quantum algorithm, except that, per epoch, you're getting 8x of that feed as a, compared to just a single circuit, which, like I said, doesn't run nearly as well in most cases. And, in any technology, you have to effectively try to break it. Like, we know there's benefits and all this stuff. So the other thing is basically best available classical algorithms versus this. So we have in the back of our heads that, like, this is, we have these extra benefits of, quantum mechanics. They, take more RAM, these types of things. So we have to compare it against every, best available classical algorithm to put in. And it shouldn't be too hard, because the, torch.nn.module, instead of putting Q laters in, put other classical algorithms in. Okay, so there's a question from Samuel in the chat, and he says, in the future, we can see the connection between QML and Genesis for Google, for example, or it's actually Gemini. Okay, the connection between Gemini for Google. Now, I'm not quite sure exactly what you're related to. I know Google Bard has posted a couple things in their blogs of using QML. And even in one of them, there's, say, like 4 other sources that say that they're using QML too. So there's, this is the practical version of QML. But yeah, you could come on. I'm not quite familiar with the Gemini for Google, so you can either put in the chat or you know, unmute yourself. And if you haven't seen the past couple, on November 13th of this year, so 2023, there were 3 articles. The first one was Terra Quantum and NVIDIA. The second was Classic in a hospital in Tel Aviv. This is all using GPUs and quantum algorithms. And the third was BASF and NVIDIA. So that all happened in the same day. So I think that was kind of like the breakthrough point. And another colleague put up on the, on their, post on LinkedIn that said, what would you like to see more, with quantum and whatever. And I said, results, right? Because we have to, this version of quantum inspired machine learning, how we have today, is not what it's going to be in 6 months, right? And for any technology like that, the field has to work together. And QEDC, Quantum Economic Development Consortium, it's under NIST, basically in the government, they do that same thing, right? Like if the technology doesn't work at all, it doesn't do anybody any good. So effectively have these consortiums to bring people together and say, okay, this doesn't work here, we need to fix this. Or say like the PyTorch or the Keras is not working with PennyLane or Qiskit with GPUs, it's only working with CPUs or mostly just CPUs. Those types of things, right? Because the results will drive it, right? If more good results, as of the ones that were presented today, if these keep coming out, there'll be more of these resources, shifting towards running quantum algorithms with GPUs and making things compatible. And this might be optimistic, but if it's basically the same issues that classical algorithms have, and now we're just have quantum mechanics, involved, but this is all done classically. So there's really no reason why anything should not be compatible in the future, right? We're talking like, it's a lot closer to apples and apples as other parts of the technology. And then anybody that we haven't heard from. And again, so you can come on, if you came on the first time. So I see a number of familiar faces here too. And it'd be good to hear, status updates on your own kind of quantum ventures, how those are going too. And things like quantum algorithms are very universal, across different aspects of the technology. So, I just, the whole thing with all of this is, yes, I would say, if you were to go to learn machine learning, it would probably be a little less confusing to learn quantum inspired machine learning, or QML with GPUs, however you want to say it. And I just want to tell you now is basically after going through all these demos, from Qiskit and PennyLane, a couple times, and then really focusing in on the parallel algorithms today and the past couple of weeks, is that it's really not that bad, right? If you understand if you're used to running these late night experiments with machine learning, it's that same kind of thing. And many times, like say, for instance, I don't have to change the quantum algorithm and I'm varying the learning rate or I'm varying the batch size. And if you don't fully understand them and, what to put in like the QML.ry or, whatever angle embeddings, these types of things, trainable layers, these types, you could ask somebody, right? And they'll say, oh, just run these 3 different types and then you're up and running, right? So you're running quantum algorithms. And I guess the other stuff is, that's all, if you're doing stuff in parallel, you're talking about algorithms. So again, I cannot stress enough, if your individual algorithm does not run well, don't start scaling it up, Okay, so don't start adding more and more layers. Okay. And, the architectures themselves, I'm calling it effective qubits. So if you have like 2-qubit circuits, like 40 of them, so that's 80 effective qubits. And then you're taking the mass effect of all these quantum effects of this 80 effective qubits that you couldn't have run with a single 80-qubit circuit. Then, this is something new, right? This is something that you couldn't originally do easily. Anything else? Any other questions? So we touched, PyTorch, Keras. We could talk about either of those libraries. We talked about, PennyLane and Qiskit. Now we didn't talk about Qiskit too much. And I would say, because of a question I asked on the Qiskit, Slack channel, is they said there's more machine learning demos coming out, and the ones they have today are good. But it'd be good to see that drive, especially as we see that, that push to running, quantum algorithms on GPUs to have more demos. Now, if you were late to join, if you have your own user data, meaning you have your own, patient data, definitely use the quantum transfer learning demo. It's just one line of code, link it to your Google Drive. You have to mount your drive first, and then you just link it and whatever. You can also do, if you're looking for speed, it's definitely these, the graph embedding demos, or it's a PennyLane, NumPy, no PyTorch, no Keras, to really, tap into these GP or lightning.gpu. It's typically faster than lightning.cocos, but the lightning.cocos, it's Kokkos CPU, is typically faster than the lightning.qubit. Okay. So, in this discussion here, this presentation will be up. And again, I have a couple more things to adjust with it. But yeah, these are good guides, and, just, you have to start running, right? And I'd be interested too, from other people, your kind of experience with this Qiskit, PennyLane, it's not quite that bad. You're going to have to put in some long days in any kind of new technology that's new to you, but it's really not rocket science. Like, getting into this stuff, quantum inspired machine learning, I would not call rocket science. Okay. And this is a good thing, right? Awesome. So Samuel put in the chat, I saw this too, and I haven't looked into it. IBM, February of next year, so in 2 months, we'll have Qiskit 1.0. Now, I think 1.0 is typically a beta, so it's like a real thing, right? So I think PennyLane's still at point something, and that it's big news, right? To go to 1.0 for something. So the really positive thing about Qiskit is there's ways of doing anything, right? There's typically like many ways. And sometimes if you're looking to do something, there's 3 different ways of doing things, and you're trying to get one of them to work, then it's a challenge. But there are experts out there that could probably vouch where they say the same thing I say about PennyLane, and where it's not that bad, right? So, but yeah, I appreciate you sharing the news there, Samuel. And it's a good thing for the industry, right? To go into something, and Qiskit is I go on the, Slack. Qiskit is, this big community, and I would say it's probably overwhelmed by users at this point. And the PennyLane one is more, they're developers, and but there's a lot more, say, working behind Qiskit and different things you can do. Awesome. Any other last comments or questions here? Appreciate
This
everybody
was
coming.
really good. This was
Oh,
really
thank
good,
you.
Kevin, Sergey, Robin. Just one more question.
Yeah, go ahead.
If I'm to look at kind of interested in you know drug discovery per se in using quantum machine learning. Any advice you have?
Well, as I alluded to before, is start with the basics. You could just do a bunch of random stuff, but it's just very scientific method kind of stuff. Like,
Okay.
Have a fixed algorithm and have a fixed model. Okay, with a fixed algorithm, just change the learning rate like 10 times. Okay.
Okay.
Save all those, save the data. Okay. You only want to change one variable at a time. And then, so the next 10 sets are going to be, change the batch size and, only changing one variable at the same time. Now, when you go time, put it in the tables, and especially when you go to chart it, you will learn a lot of stuff about the model, right? Say for instance, if I'm doing single circuits with, variable learning rates and it's all over, but I do parallel circuits and it's very constant across a broad range. This is indicating a good architecture, right? And that two same algorithms, single circuit or parallel. But I would say that because the flashy thing to do is just to like, oh, the most images in my data set better than anybody else, or I've done the most classes, these types of things. But it's a very cumulative thing, right? So when you get to the point of understanding quantum algorithms more, then you can say like for an embedding, layers, just add another embedding layer and then do 1 through 10, something like that. And like I said, it sounds so trivial, but it's really the hard work that many people don't do because they just like, they just randomly haphaz to like 6 layers and say you didn't do 1 through 5. And in fact, it was 4, that was the best, right? So you missed out on some performance there because you didn't do the comprehensive study. So yeah, I would say, machine learning, quantum machine learning is the same thing as you really want to, you'll learn a lot more by being, diligent and organized, saving every notebook, Python notebook, these are all in Python. And then, I always save a PDF too, those types of things, because the optimizer, loss function, all those other things, are universal to machine learning. And then, once you get, like I said, to the point where you understand, okay, if I add, trainable gates here as opposed to embedding gates, or if I want to introduce entanglement, those types of things.
Sure. No, thanks, Kevin. So essentially, I should be incremental in the approach, the way we do it in the traditional machine learning.
Yeah. It's the same thing with anything. It's like, your chances of finding something that's new are a lot better if you're very, organized, those types of things, because, some might say like, oh yeah, running parallels and algorithms, this has been done classically, but then proving it in quantum and talking about the minutiae of, quantum layers and different algorithms and those types of things, they're a little different, they're a little different. But yeah, that's what I say is basically really start off with the basics that and then do a good job of, charting all of that and actually, making the charts, and then, kind of easing your way into the algorithm modifications or architecture too.
Yeah. Thanks, Kevin.
Yeah. Anybody else? Appreciate everybody coming on. And again, so this has been discussion 114, Thursday, December 21st, for how to conduct medical R&D with QiML algorithms and architectures. So, there's definitely enough to get started, especially with quantum transfer learning, parallel algorithms. You're going to have to do some fundamental, research, meaning that working with other data that's not your data set, up front for many of the models. But still, getting ready for that time to insert yours. Awesome. Appreciate everybody coming on. Thanks again. And have a good night. Have a productive rest of the week. Take care, everybody. Bye.